All right, so today we're going to continue the discussion on graphical model structures. We're going to talk about another very big family of graphical models known as Bayesian networks. Okay. Oh, by the way, have you guys all already have access to the videos of the class? Is that helpful? Actually, I also wrote my notes, sometimes on the slides. Do you want that as well to be posted? Yeah. All right, I'm going to, in the future, post two versions. One is the clean version, the other is the scripted version, okay? All right. So, just a recap. Now we know that there are two types of graphical models. Last time we saw this type, which is the undirected graphic models. It captures some kind of simple relationships between random variables, which are kind of associativeness between pairs. And then, by ways of defining potential functions on cliques, in which every clique or every potential is able to accommodate all dependencies between random variables in a clique. That is what the clique is meant to be, right? And once you capture all that and multiply them together, you get a probabilistic distribution which encapsulates all the dependence or conditional independencies within this undirected graph. Okay? And we mentioned already a little bit about the completeness and soundness of this technique in terms that the dependencies that you can read off from this graph, the independencies you can read off this graph using something called a Markov blanket local dependency definition. And also you can prove or derive the independencies from the distributions. They are kind of equivalent, right? But we didn't prove that. Today we're going to dive a little bit more into the more richer type of graphical models known as the directed graph models, where you see how to again capture very rich set of relationship between random variables, and then still make sure that the probabilistic distribution and the graph semantics are equivalent. So here is a directed graph model. I put all the edges and the arrows. This is a graph actually I showed in class 1. And then there is a corresponding, way of writing down a factored version of the joint distribution. Okay. And you actually can probably see something already from here, but I'm going to state more clearly about what that factorization law is in a few slides. Okay. So here, we are going to also introduce the concept of knowledge engineering. In a sense, why graphical models or Bayesian networks are particularly interesting in the world of multivariate modeling. It's because it gives you a very, very flexible way of engineer your knowledge, to encode your knowledge in a very flexible way, much more kind of flexible and richer than the undirected graphical models. We already see this graph. If you remember, this was a graph kind of expressing a biological story. I'm going to show you a few more examples so that you can get a sense about how knowledge engineering, or how we take advantage of the directed graph model to perform very flexible and expressive knowledge engineering. In fact, nowadays, with the prevalence of deep neural networks, very complex deep models, without a graph as the kind of the vehicle to express and to communicate your knowledge, it's very hard to design bigger models like that. So in a sense, graphic model provides the initial vehicle, for people to build very complex models. So just give you a very historical account. For example, here you see one graphical model, which was published a long time ago. Okay, and in fact, one of the co-authors is Greg Cooper, who is a very, very accomplished professor here at UPenn. We collaborate a lot. He was one of the pioneers in this field, along with quite a few co-authors and colleagues. For example, such as David Hackerman, for example, and Eric Horowitz, who is now director of Microsoft Research. They were actually all pioneers in this field. And this graph is literally about knowledge engineering. It's a effort to create an expert system using, probabilistic theories. And each node represents some medical phenomena, symptoms, causes, consequences, and so forth. And then, because you can see many of the authors are MD, PhDs, in the sense that they know both the medical knowledge and also the computer science statistic knowledge, they were able to, introduce some probabilistic, description or qualifications of those knowledge, such as what is the probability of developing a symptom given some cause, something like that. But to a medical doctor, they have a much bigger picture about the clinical domain than a average individual. So they were able to build a large graph and then synthesize all these knowledges into a coherent model, which is what we are going to see, a joint probability distribution of all these random variables. And you will see very soon that the Bayesian network offers such a convenient language to just perform this synthesis. And as a result, by using this graph model, you can ask all sorts of interesting queries, such as the conditional probability of a particular event, which is one particular random variable in this graph, given some other events. It could be a subset of random variables in anywhere of this graph. So this is a problem called inference. And with a graph, you will find that inference becomes a lot easier than just performing analytical calculation, giving a big table of joint probabilities. Okay? So that's one example. The second example, I'm going to walk through you even more closely so that you can appreciate how fun it is actually to build a model. And your project may start exactly from a exercise like this. You have a bag of knowledge of a real world phenomenon, and then you are going to just step by step compose or synthesize a model, and then you are going to land at a pretty big probabilistic knowledge base that allow you to do queries and allow you to do a lot of other things. Okay, so and that actually also give you the essence of the kind of the spirit behind graphical models. Many people thought graphical models is a highly theoretical, technical kind of in topic, and this class has been viewed as one of the most difficult theoretically course in the program. But the truth is that graphical models from day one is aimed at solving very practical problems in real world. Okay, you really want to build a bridge of a complex real world into and also the mathematical expression and the vehicle of that, and then you can hopefully provide some rigor and also some convenience into your practice. So let's look at this real world. It's a quite fun real world, right? Have you guys went to Atlantic City or Las Vegas during the break? Did you? At least during the winter break, not the Martin Luther King break, right? Well, you can imagine at least that you go to such a place. You may want to play a few games with a dealer like this, right? He has stacks of chips, and you play a very simple game like roll the dice and then compare the points, okay, as an outcome. And you shouldn't having too high expectation on the fairness of a casino, right? So you probably should be prepared for this guy owning two type of dice. One is a fair die, which has an equal probability of all faces, and the other one is a loaded die. He could be loading the die in that way that 6 has a half of the probability, and all the others split the other half. Okay, just this is a scenario. In fact, this is part of your knowledge about the domain, how someone told you about so. And then here is the rule of the game. You can read it. And I guess by intuition, you want to make sure that you roll and he roll, and you want to get more 6 as many as possible. So that's kind of the possible world, this honest casino that you are going to enter. Okay, so here are a few puzzles that you may want to establish some formal theory or maybe some reasoning technique, to help you win, or at least to help you avoid losing. For example, after playing, say, 50 rounds, you saw this sequence. You may start to ask, am I dealing with a fair dealer or a tricky dealer? And the only evidence you have are the outcomes of the 50 roses. What do you conclude after just tabulating the results and seeing all that? I'm training you guys to be a geek, okay, a mathematician or a computer scientist, rather than an average tourist into the casino. So when you see this, what do you feel? Someone want to suggest a observation? Yes, please.
The 6s are super common.
Yeah, 6 are super common. I highlighted them. You can see that maybe, roughly a half of them are 6, almost, right? So this is a little bit counter-intuitive because if you have a fair die, you should see all numbers equally common. Then, because we are CMU graduate students, we want to be a little bit more quantitative and formal. Let's ask the following question. For example, the first question would be, how likely this sequence, is, given that we know that how the casino work. For example, we know that there are, 2 type of dices, and the probability of the outcome and so on and so forth. Do you want to actually make a mathematical calculation about the joint probability of this whole thing, right? So that's a question that you can ask. And in fact, why it's interesting because you can compute the joint probability of all different, sequences. And then you can actually even conclude which is more likely, which is more unfair. Right? So this is known as the evaluation question, which literally amounts to compute this value. Right? And then if you want to be a little bit more aggressive, you could even start to ask which of these 6s or even other numbers are produced by a fair die, and which portion are from the loaded die. Okay, so this is a legitimate question. You want to really, kind of see through, what is happening, out of a phenomenon. Right. So this is known as a decoding question. It's about the conditional probability of, say, let's say, x of 20. The 20 is placed in somewhere here, given, some choice of the dice, right? Or maybe you can ask the reverse. What is the probability of y of 20, which is the choice of the die over there, given the entire thing? Okay. And then you could be even more aggressive and want to outsmart the dealer, so that you can basically choose to bet, based on your estimation, okay, of the events. In the sense that you want to learn how likely, what's the bias of every dice, and what's the tactic that the dealer is using in switching between loaded and unloaded, right? So this is about learning some of the numbers behind the probability distribution, and this is known as the learning question. Okay, so this is your problem and your environment. You have a bunch of knowledge. So how do you start, a task, given that you graduated from the graphical model class? Okay, So this is basically giving you a example about how we perform knowledge engineering with the help of graphical models. First of all, you need to pick random variables which correspond to the events of interest that you want to say something about. So what are the events of interest that you care? The
type of the dice.
Okay, you care already the type of dices, and but obviously you also care about the outcome of the dices, right? So which is the numbers you actually see. Yeah, you can see that there are two types of variables that you already care about. X, which is the faces of all these dices, right? And also Y's, which correspond to the choice of the dices, right? Let's index them to be I, meaning that you have the ith row of that. And these are the random variables. There are other things, the location of the casino, for example. You can make it even bigger, but for the sake of simplicity, let's focus on the most interesting random variables or events. And then you can already build some structures into this using your knowledge about the physical world. For example, the outcome of the dice is coming out of the choice of the dice, right? Therefore, there should be some kind of a causal structure. It's not a correlation, right? It's not that the outcome kind of determines the choice of the dice, right? So it's not symmetric. All right, and then actually I'm jumping ahead of me already. I'm not yet ready to pick structure. I want to still say something more about that. So every random variable has to have a scope and also the possible choices of their values. So what is the domain of X? Well, it should be anywhere 1, 2, 3 to 6, right? And Y should have a scope as well. I should have a domain as well. What is that? We should probably make them fair and loaded, right? And now, of course, you can put a categorical kind of number, say 1 or 2 or 0 and 1, so forth, to represent that. So, in a sense, every random variable, you have to decide, first of all, by the way, you observe the X, but you actually don't observe the Y directly unless someone tells you, right? So we want to make the graphical model a little bit more colorful by distinguishing the two types. We shade those nodes or rather variables which are directly observed. We call them data, right? And we leave the other one unobserved to be empty, and they are also known as latent random variables. Okay, and then every random variable could be discrete and continuous. It really depends on what you measure. In this case, all the events are discrete, but it could be also continuous. For example, it could be continuous between minus infinity to positive infinity. If you measure something, I don't know, the temperature of the universe, something like that. Right. Okay, and after you pick the random variables, you are going to pick the structure, and here is one structure. And it could be causal, it could be generative, it could also be coupling, which is the case for our undirected graphic models. Right. In this case, maybe we should call them generative rather than causal. Right. And in fact, you can build more structures in here. For example, you are not coming here to roll just once, right? Let's say we are going to roll 20 times. How to express that structure? Well, maybe we should do this. Y1 gave rise to x1, y2 gave rise to x2, and y3 to x3, all the way to y20 and x20. Okay, so this is a structure. This is a graphic model. Isn't that a graph? You have edges and you have nodes. Do you want to add something more to that structure? In here, you can see that the y's are independent. Okay, my next choice of the dice has nothing to do with my previous choice. And also the outcome of that choice is not dependent on the previous one. Well, some dumb dealers may exactly do that, okay, but that doesn't give them a good chance to win. Well, still some chance because there is, after all, a loaded die. Once you pick that, you are likely to win more, right? What if you are the tricky dealer? Do you want to be a little bit more strategic? I think there are two purposes, at least, for being strategic. One is that you want to increase your chance to win, but also you don't want to be called out, by the player. Because if you are too aggressive, you just don't switch. You keep using the loaded one. I don't think you can pass 10 games. You will be called out, right? So what's your strategy? Okay, I will suggest one. Maybe after all, my choice of the next die should be at least depending on my choice of this one. For example, I'm going to choose the next die to be the same, with a high probability. Okay, if my current die is a fair one. I'm using a fair dice, then with a 0.99, I'm going to choose again, a fair die. And then I'm going to have a very small probability, 0.01 or 0.1, to pick the fair one. So what's the advantage of that? It's very difficult to catch you because after all, you don't use the loaded one very often, right? So that's actually a knowledge. Okay, so your second one will be dependent on the first one, and you can also draw this. You could, of course, be a little bit more sophisticated by saying that my third one depends on not only the second one, but also the first one. You can actually build that as well, if you really want, right? Okay, so this is basically the structure of, the random variables. And then you also need to define, the probabilities. For example, how to express the fact that a fair die has equal probability of all the faces. Well, that's represented by the conditional probability of xi given yi, right? Equals to f, and p of xi, yi equals to l. These two probabilities, right? In fact, for all the i's. How to express my policy or my strategy in picking the dice? Okay, I want you guys to get used to the language or the expression of your knowledge using probabilistic language. You do this. You basically say, my yi plus 1 given yi is something. Right? That basically defines a conditional probability. And in fact, you can say, I'm going to be stationary. That's another word. Stationary means that for the entire game, I'm going to use the same strategy. Therefore, this transitional probability is going to be good for all the i's. Right. You can also be non-stationary by saying that, for every I, I'm going to change my probability. Well, that's going to be very hard to implement because you don't even remember what you'll do, right? So it's very hard to really be accountable. So anyway, so these are just examples of knowledge engineering. Okay, at the end of the day, you have random variables, you have structures among random variables, you have also this local conditional probability of between random variables, and that leads you to a model. Okay, and this model is known as the very famous hidden Markov model. Right? The underlying sequence, the underlying source are hidden, and in our previous example, they correspond to dice choices. But you can imagine, and in fact, the outcome corresponds to the sequence of rows. But for more valuable applications, you can imagine they correspond to maybe a line of DNA sequences, and then the hidden variable correspond to whether you are in the region of a gene, encoding region, or in the so-called junk region where it's just doing nothing, other than supporting the structure, right? You could also make a speech recognition or speech synthesis where these guys are the phonemes and these guys correspond to the speech signals. Okay? And you name it. There are many, many examples of this. Right. All right. So once you have this structure, what you achieve, what you can do? Well, it helps you to now write down an extremely, extremely informative and also useful joint distribution of all these random variables. Useful by useful I mean they are more useful than the gigantic table of all these random variables. Okay, without assuming any structure. Okay, so let's see how that can be established. We have a graphical model now, which is a HMM. The structure now become hopefully intuitive and explainable to you. And also it's your creation, basically. You put the structures like this based on your knowledge. Then I'm having two sets of data. One is the row outcomes. The other is the dice choices. And the joint probability of this is what? Okay. It turns out that because of the structure that you lay out like this, you can write down the joint probability using very, very simple manner, which is to just multiply together all these little terms. P of y1, which is this guy. P of x1 given y1, which is this guy. And P of y2 given y1, which is this guy. And then this guy and this guy. Okay. You literally can multiply together all these either marginal or local conditional distributions or probabilities by traversing that graph in the following sense. Every time you run into a node, you check whether it is the root without parent or it is an intermediate node with children and also with parent. Then you can plug in a term which is the marginal, okay, if it does not have any parent, or you can plug in another term which is the conditional of this node given its parent. Okay, you only need to have these two pieces and you traverse the entire graph. After you visit all the nodes, you multiply all these terms, you get the joint. Okay, so this is a factorization rule, which can be established as a theorem. Okay, you can rearrange that a little bit, and then you can also remerge them. You actually will see that this probability corresponds to the bigger factorization, which is this one, which is the probability of the hidden random variables, and the probability, conditional probability of all observed random variables given all hidden random variables. Okay. And now, once we have that, you can now make maybe try to answer some of the queries or the puzzles I stated before. Remember, one of them is the puzzle called evaluation. What is the probability of a sequence of observations, not knowing the hidden random variables, not knowing the choices of the die? You just are presented with a sequence. That basically corresponds to algebraically the marginal probability of x without y. And based on the basic theory of probability, what you need to do is that this one is the marginal distribution or marginal probability of x, okay, and y. You sum out all the y's, which means that you need to sum over all these y's, and this part are just the algebraic expression of all these conditional probabilities and marginal probabilities. Okay. Now, let me ask, how many summations you have to do, in a naive way, here and in here? So I ask all these questions again just to bring you, the sensibility to computing and to operationalizability as a computer scientist. Statisticians usually stop from here. Once I have an expression, I'm done. I'm done with my proof. Okay, but you have to implement that in the computer, and therefore you have to finish all these steps. So can you answer how many steps it takes to finish this summation?
Size of y1 times size of y2 times size of y3.
Mm-hmm. Okay. Therefore, let's say the size of y1 is k. K choices, let's say, times k times k, right? Which is giving you to k exponential, right? So it's a exponentially complex operation to do all the marginalization. And if you play the game 100 times, you will get 2 to the power of 100. How big is that? 2 to the power of 10 is already 1,000. And then you can do a cube of 1,000, which is already quite big. Okay, yeah. That actually gives you a hint about why this graphical model can be useful. I will tell you very soon that using the graphical model structure, you can reduce this quadratic complexity to actually linear or to polynomial complexity. Okay, how about we make it to be n squared, for example, something like that. Right. Okay. This is just a teaser of a trailer of the entire class down the road. I have another query, which is to answer the likelihood or to estimate the hidden sequence given the entire observation. And it is called the posterior probability of the hidden random variables given the evidence. And here is the formula. And you can see that this is a joint and this is a marginal. In fact, you have to compute this first before you can get this. Therefore, it is equally, if not more complex as the previous one. Right? Okay, so that's just give you, a very, very quick teaser of knowledge engineering and also the cost of that in a real world problem. Okay, so now let's get back to our very fundamental definition of the directed graphical models. The previous examples are meant to inspire you, for the utility and the future, questions that you may ask for this type of formalism. Now let's get back to the formalism. So Bayesian network is a directed graph model, whose nodes are representing random variables and the edges are representing direct influences among or between the random variables. Okay, and the second statement is very crucial. It is a data structure that provides the skeleton for representing the joint using a systematic factorization way. Okay, and also, it gives you compactness because instead of writing down the big joint using a gigantic table, all you need to do is now to express every local entity. One is called the marginal of some random variables, which do not have the parents, and others are the conditional probability of some other random variables given their parents. Okay, they are all small distributions. Small means that the number of random variables you have to touch is very small. Okay, and of course, operationally, you can use that as a process to sample examples, but we can cover that later. Okay, to state more formally, this is how you define a Bayesian network. And we, of course, have this issue about consistence, right? There is a graph, and there is a P. And the connection between them is through factorization law, right? But are there other ways to define a P from a graph? Or are there other ways to extract from the P some graphs? Are you going to always get the same? This is what we mean by consistency. Okay? So we are going to be a little bit more rigorous on what entails this consistency in a second. Okay, so remember this definition is very, very handy, very, very operationalizable in terms of defining distributions. And this is, again, the example. All right, so now let's look into how to specify models using this principle. We already did one for HMM. And here you have a more kind of generic one in terms of the structure. HMM is a chain. It is particularly simple because every node has only one random variable as a parent, right? And also there can be actually a little bit more. For example, there can be more complex scenario where a node may have multiple parents. These are seen in general models. So to specify a directed graph model, you need to do two things. You need to have two things. One is called the qualitative specification. The other one is called the quantitative one. Qualitative one generally refers to the structure, okay, of the graph, which is a part of the expression of the knowledge. The quantitative ones are these guys, are the local conditional probability tables. Okay, so you need to have these two pieces in place. Where do they come from? Well, the qualitative ones, in a sense, had a huge space of origins, right? It could be the prior knowledges of causal relationship, of other relationships that you know about. It could be coming from your expert friends. It could also be learned from data. We're going to say a few words about this when we are going to causal graph learning. Or maybe sometimes it's arbitrary. It could be just a way I like it. In fact, many of the deep neural networks are built to, for example, why you pick 100 layers rather than 101 layers? Well, it's kind of arbitrary, right? Why not 99, right? And also how wide the graph could be. How many nodes you need to have for a particular layer, 100 or 1,000. There are some arbitrariness there, although there are some guidelines as well. We can talk about that later. But given all this, I think there is also a need to be a little bit more rigorous. We will ask, is there a more concise and ambiguous and rigorous, at least meaning? Once I give you this graph, can we all agree on some common principles? Rather than we still walk away with 1,000 different interpretations. Right? That's no good. So on that, we need to go back to our old friend of conditional independencies between random variables, because that's where I don't think people have ambiguity in interpreting that. Something are conditionally independent. It really means that the distributions are factored in a particular way. There is no other kind of interpretations of that, right? So let's see whether this is possible. So let's begin by looking at some local structures. Okay. In this graph, you can see finite number of local structures. So here is one. It's called the common parent structure. Okay. And which is like one parent giving rise to a couple of children, and that actually corresponds to a particular type of conditional independencies. Okay, it basically says that P of A and B and C given B, okay, A and C become independent given B. Okay, which means that P of A given B and P of C given B can be multiplied. Okay, so this is guaranteed. I'm going to prove that it's guaranteed if you write down your joint distribution using graphical models. Okay, this graph gives you that kind of this graph motif gives you that kind of independencies. And again, this is a very common natural kind of pattern of causality, right? A particular gene triggers, for example, multiple downstream genes. The other graph motif, such as you see from here, is the cascade. Okay, in the cascade, you see at least 3 random variables. Then the conditional independence is that given the middle one, if the middle one is already observed, then the previous one and the future one become decoupled. Okay. I'm going to leave it to you to write down how to express that in probability. Okay, P of equals to what? And again, this is in English you can say that the past is the future is independent of the past given the present. Very philosophical, but it's true. Right. The third one is a little bit tricky. It's called the V structure. I think you saw it from here. Okay. It says that the 2 random variables are originally independent. For example, A and B are actually independent if I have nothing else to say about the model. Okay. However, if A and B are given a piece of new evidence C, okay, suddenly, A and B given C are not independent anymore. Okay, so this is a very, very interesting phenomenon, which is a little bit tricky to appreciate. So I'll give you an example. Okay, I'm going to establish 2 events first. So there is a clock at the back of the wall which says now 12:44. Okay, and we can qualify that clock to be sharp or inaccurate. Okay, so it's a binary event. I can also put another event, which is the traffic condition on Highland Park Bridge, which happens to be, on my way to school. Okay, so that's an event. So these 2 events, a clock being sharp or not here, and the traffic jam taking place or not on Highland Park Bridge, what do you feel about these 2 events? Are they dependent? Surely they're not, right? But I give you a third event. Given that you know some knowledge already, it is a bridge really, on my way to here. And also here is a clock which is in here. Now I have a third event, which is I show up in classroom on time or not. Okay, that's a third event. Now, you come here 12 o'clock, and you wait for 10 minutes, and I didn't show up. Okay, now I want to ask whether, the clock being sharp and the traffic being jammed, are these 2 events become coupled? I think it's coupled, right? For example, if, through searching Google Map, you knew that, there is indeed a traffic jam out there, then I think your conclusion on the quality of this clock will lean toward the clock maybe is okay, right? But if you knew that there hasn't been any traffic in the bridge, maybe everywhere, then your suspicion about the clock quality may be changing. You may say that the clock has some problem, probably, right? So these 2 events gets competing for the same consequences, which is my absence in the classroom. They compete for explaining that. Once you know one part of the explanation for sure, then the assessment of the other piece of the contribution is going to be changing, right? So this is called the so-called the explain away kind of phenomenon, and which is again a very common phenomenon or pattern of reasoning in real life. Okay, I claim that these 3 motifs are pretty much enough to serve as the building blocks of all our probabilistic graphical models or direct graphical models. Okay. Okay. Any questions so far? So these are nice building blocks, and just to give you an easy way to, in terms of how to prove them. These are very, very easy proof. For example, the previous one, the first one, called the common effects. We want to basically establish P of A and C given B is equal to P of A and given B times P of A given C given B. Right? We want to ask that is true or not. And then what's the given? The given is that my joint of A and B and C follows a graphical model definition, a Bayesian network definition, which is that it equals to P of B times P of A given B times P of C given B. Right? So this is by definition, okay, of a graphical model. And can we prove from here to here? Right? Should be straightforward. P of A and C given B equals to P of A, B, C divided by P of B, right? And again, by definition, the upstairs equals to P of B times P of A given B, P of C given B divided by P of B. These two term cancels, and you get that. Very trivial. You can imagine that you can apply this very, very tedious exercise to larger graphic models of arbitrary sizes. I'm going to guarantee you that all the conditional independencies can be proved like this once you use this Bayesian network or this factorization law to define the joint. Okay. Okay, so that gives you a, now going back to the IMAP. Remember, IMAP is the little kind of device we use to establish the relationship between a graph and a distribution. And in particular, for a graph, you can always extract, all the conditional independencies using some graph rules, right? Such as the three little local, independence rules I just presented. You can scan a graph like that and get all that. And then algebraically or analytically, you can imagine that there exists a set of independencies for an arbitrary probabilistic distribution. And now let's ask, are they equivalent or not? If my distribution comes out of a G, for example, are they equivalent or not? And we saw this before. Let's skip that. Basically the quality of the IMAP, it's only going to be meaningful if once you have a IMAP, it's not going to suggest anything more than basically that graph should suggest. So we ran these examples before already. Let's pass that. Now let's really ask what is in the IMAP of a directed graphical models. So we used this so-called local Markov assumptions, okay? And let's expand that a little bit, okay? And it is actually very easy to show you the following, local conditional independence assumptions or sets from a graph. It includes the following collection of independencies, which is that for every random variable xi, or you can also understand that as every set of random variables, but it's easier to start with singleton. This guy is going to be independent of its non-descendant given their parents. Okay, so go look at the graph, identify a node, and also their parents. You can safely claim that X is going to be independent of all its non-descendant. Okay, not basically anything downstream of the graph, not directly upstream because they are the parents. Anything else is going to be independent of xi given the parents. You can run this micro or this oracle for all the graph and get a set, and that's called the I set or I local of G. Okay. Okay, so that gives you AI. Okay. It's a little bit inconvenient to use this local Markov assumption to extract everything, because sometimes you want to arbitrarily choose 3 sets in the graphical model to ask for their conditional independencies, which may not just be parents, myself, and my non-descendant. It could be arbitrarily 3, right? So for that, you are essentially asking a broader global Markov independence problem. And here we need to use a little bit more trick. Remember, in the undirected graph model, if you remember, what is the property of the global Markov property, if you still remember? If I have 3 sets, x and y and z, how can we establish x independent of y given z, if you still remember? Mm-hmm.
No edge between, direct edge between x and y.
No direct edge. Well, I'm asking any arbitrary 3 sets. There is a broader definition about the separation. Uh-huh. Markov blanket is for local, remember? Yeah. Yeah.
If any nodes that you connect x and y or any paths between x and y are in the set of z.
Yeah, so you're talking something like a graph separation, right? So basically, I have this set x, I have this set y, and there's a little one z. And as long as any path from x to y is blocked by z, this one would be honored, right? So in a sense, you want z to be the graph separator between x and y. And on undirect graph models, graph separation is very, very trivial, right? Now we have a directed graph model, which is a little bit tricky. So we want to do a little bit more about that. It is no longer called graph separation. It's called a D-separation, okay? Directed separation. And here is the definition about arbitrary 3 sets when they satisfy a D-separation statement, okay? The definition reads like follows. It's a little bit strange, okay? The variables x and y are D-separated, or in another word, conditionally independent, given z, if they are graphically separated in the moralized ancestral graph. Okay, so we walk back into the standard graph separation, but in a different graph. It's called the moralized ancestral graph, which is undirected. So it is not the original graph. Because we love this separation thing so much, it's very, very easy to define and unambiguous. Therefore, we keep that term as the qualifier, but we engineer the graph a little bit so that that term can still be operated. What is an ancestral moralized graph? That's a little bit tricky. So here is the original graph. You have all these edges. You have random variables. One is given to be conditioned on. The ancestral graph first asks you to literally remove, let's see, x, y, and z. To keep only those elements which are the random variables themselves of interest and their ancestors. Okay, that's called ancestral graph. So as a result, this guy is gone because it is not an ancestor of any of this. Okay? It's still a direct graph, but only contain the variables of interest plus their ancestors. Okay? And then you do another kind of interesting operation called the moralization, 2 steps. You drop all the errors of the edges to make them undirected. And then you marry the pairs which were originally unconnected in the original graph. Okay, so why it's called moral? At least in their definition, they believe that if two parents are not married and give rise to a children, it's not very moral. Therefore, they will have to moralize that. Okay, so that's called ancestral moralized graph. And then your graph is now converted from this one to that one. This is an undirected graphical model or undirected graph. And in here, you can apply graph separation. You ask, is X and Y still graphically separated by Z? Is it or not? In this case. Well, obviously, Z fails to graph separate X and Y because there is an edge here already, right? Okay. And you can kind of almost walk back and see why this is the case. Because here we are looking at a V structure, right? The common, this one and this one shares a common descendant, which is conditioned. Therefore, this and this become coupled. And because this and this is coupled, and this one is coupled, therefore this one is also coupled. So there is a transduction basically of of influences using this V structure, to bridge basically remote dependencies. Okay. In a sense, you can use this rule already to implement a little program to scan the graph and get all the independencies. I can make it a little bit more easy by proposing literally an algorithm called the baseball, which literally just did the same without even asking you to, because creating a ancestor moralized graph is still cumbersome, right? What if I still want to just keep staying on the original graph without creating any new one? Well, with the baseball algorithm, this is possible. You basically want to run 3 processes on the graph. By imagine that this graph got hang like this. You just hang it vertically, and you want to pick a origin, where stands for your X. Okay, one of the set you want to ask a independence query. You drop a little ball into the network. Okay. And the ball will be bouncing back and forth and hopefully move to the other end of the graph. And you will see, you ask whether my ball can reach to Y in the presence of, in this case, reach to Z. Okay, here, sorry, there's a notational ambiguity. I'm asking the following query. Okay, can reach Z given Y? Not. And here is the rule. If Z Y is in the middle between X and Z, in this configuration, there is an edge into Z and an edge out of Z, and Y is observed. Then the ball will bounce back and couldn't pass. Okay, if Y is not observed or not being conditioned, then the ball can pass. Okay, so that's one rule. The other rule is that if Y stands as the common parent of 2 Y's, X and Z's, then again, it is going to be bouncing like this. And it will let go if Y is not being conditioned now. You may ask, what if I have something like this, Y, and I have a bunch of other things in here. And here is X, here is Z. Well, in that case, you need to be smarter because in here, you are talking about this rule. And in here, you are talking about this rule, right? So it's a very local operation. You just pass a little ball like this. And every time you run into the next node, you ask whether this condition is met or that or this and that. Okay. The third one, which corresponds to the V structure, is a little bit counterintuitive. If this guy, the common parent, is being conditioned on or observed, actually it let go, let pass the ball. and otherwise it will bounce, okay, which is the opposite of this. Again, so the beauty of this rule is that they are all very local. Okay, local means that local means cheap, right? Whenever you do an operation, you don't have to examine the entire graph. You just basically look at what you have, as of now, and decide whether to go up or a block. So once you do that, for every triplets in the graph, you are going to collect this set, and this set is basically the I set, okay, the IMAP of the graph, and this is called the graph, the deep separation. Okay, so I meant to do live, about getting IG for this graph with all possible queries that you can ask. But because of the interest of time, I'm going to leave this to the scriber today. Do we have a scriber today? I bet some of you will be doing that. And then, you will be presenting that in the notes and other people can study this, okay? All right, so now let's converge to something a little bit more cleaner and condensed and more formal. So we know that the separation properties can imply the independence properties about the variables. So let's look at the equivalence property. You have you can now start from a family of all distributions which satisfies this. Okay. Basically, a graph, by using the baseball rule or other rules, you get a set of independencies, and you can imagine behind that there could be a family of distributions satisfying that. And then the other alternative is that without going through all the G's, all the independencies, you just directly use the factorization law to mechanically assemble a distribution like this. And again, there is a family. Why there's a family? You can have all different numbers, put into this table, right? So you have many infinite, but they are going to be composed together, to build this joint. Which one is convenient? Well, certainly this one is very convenient, right? It's also very local. The good news is that these two families are the same. Okay? Basically, once you have a graph, you don't have to now, there are a whole rich set of conditional independencies out there, and if you need to, you can extract one and tell people a story. But when you are building the distribution, you can only use the factorization rule to do this mechanically. They guarantee you that all these independencies are honored. Okay? So it's a very, remember in the undirected graph model, we have a counterpart theorem, which is called, if you still remember, which also allow you to start with a graph, right? And use all the cliques, define potentials, and then come up with a joint. And I said that the independence over there are also equivalent to all the independencies, in the graph. What is that law? It's called the Hammerschmidt-Clifford theorem, right? Which guarantees you a Gibbs distribution form, which correspond to the multiplication law in here. Okay. All right. Let's unwind a little bit before coming back condensed again. Let's just do some exercise. Okay. So here I have a graphical model like this. Let's begin by something simple. They are all discrete random variables. How can we build a joint like this? Okay, very simple. You literally just put the tables like this. Okay. You may wonder, where are these numbers come from? Okay, that's a whole big universe of a topic. We can learn them from data, or we can just ask a friend who happen to know the facts, know God's rule, and they will give you those numbers. Okay? And the joint is produced by multiplying together. Equally interesting, if not more, is the case of continuous probability distribution where you don't have a probability tables anymore. You probably need to work with density functions. Okay, and here are just examples of how to combine continuous distributions. Okay, and how to define conditional distributions in the continuous space, given parents and given other things. So marginals are very, very easy, right? You have these two continuous random variable. Say we want them to be Gaussian. Okay. Again, this is by remember here, no distribution, are really true, but they are useful, right? So here you choose them to be Gaussian. It's not like they are Gaussian. Okay, you model them with Gaussian. Just like in this case, you choose them to be discrete, or binary, Bernoulli or multinomial. But in real life, are really like that? I don't know yet. Here is a little trick. If you want a third random variable, continuous one, to be dependent on two other continuous random variable, how do you form the dependencies? Well, here we have additive dependencies. The mean of this guy equals to the sum of the two means of the previous one. In fact, you can also propose to make them the dot product between these two. That's also fine, if this is a one-dimensional random variable. And there are other ways, but here comes to the effort of design, your choice. Okay, the choice can be factual, can be need-based, also can be computational limited. And here I have yet another random variable, continuous one, dependent on the previous random variable, just single one. Or I can choose to offset the mean by some other constant, another idea. So at the end of the day, you will have a joint distribution of multiple random variables. You may ask, what if I put yet another random variable which is discrete? Have you thought about that? How a continuous random variable depend on a discrete random variable? Yeah, threshold could be one, right? If y is 1, I choose them to be uniform and random between 0 and 1. Otherwise, it could be uniform random between 1 and 2, right? So very arbitrary. So this is really part of the engineering. A common choice in here, if it is discrete, is that it becomes a switching random variable. Okay, I have multiple Gaussian models in here. I'm going to switch between the three, depending on y equals to 1 or 2 or 3. That's another thing. This idea has been used for clustering data. Okay. All right, so here is a summary. It's an important take-home message. I'm not going to read, but I think we went pretty in-depth. Maybe we can ask this question. Previous ones are pretty straightforward. Now, I'm going to have a P, okay, which say I derived out of a graph using factorization rule. Okay, so let's call them P of F given G. Okay. Are you curious about the possibility of additional independencies in this P? It's very overloaded now with multiple brackets. Does this I have something more than the I of G, which is extracted using my baseball algorithm? What's your guess? Okay, so this is becoming a little bit more interesting. Yeah, so here let's make it a little bit more formal in terms of the soundness and completeness. Again, for a full account, you can read Daphne Kohler's book. They have a pretty detailed chapter discussing this whole stuff, which I found to be very interesting, but difficult to read, I have to be honest. So here I extracted the essence from that in 1 or 2 pages, so that you can at least pretend to be knowledgeable in the future for this completeness and soundness. It turns out that there are some leaky places which prevent them to be totally complete and sound. Well, as a matter of fact, the soundness is actually good. If you have a distribution P that factorizes over the G, then you are guaranteed that all the i's of G, all the independencies due to the Bayes law, the Bayes law, from the graph, is actually honored. They are all honored in the I of P. This part is safe. Okay? In the sense that the graph isn't going to give you additional explanations, additional independencies that is not captured in the graph. This is very important because you started from a graph, you write a distribution, and you tell people usually a story based on graph. You never tell a story based on numbers or P to people, right? And you want to make sure that I have my faith that when I read the graph and tell all the independencies, they are all honored in my P already, even though I don't have time to check those numbers in P. Right? This part is guaranteed. The reverse part is unfortunately a little bit problematic, which says that if I have a P which comes out of the G using the factorization, then if numerically in the P I extract this conditional, again, so given a P of X and Y and Z, you can somehow extract or test whether this independence is true or not, just on the numbers, right? And if you somehow test it that there is a independence like this in P, do you expect to see the deseparation of these three in the graph? So I'm going reverse now. I said that if you tell the story from graph, they will be always in the P. Now I want to tell a story, although very, very few people do that. But imagine I can do it, by just screening the numbers in the P, okay, enumerating all possible configurations of P, and I get an independence like this. Then can I go back to the graph and say, hey, these three sets must be deseparated graphically? Okay. It turns out that this is not guaranteed. Okay, not guaranteed for, fortunately, some few special cases. And the proof of this is actually very, very tricky. It's very interesting. And here is a proof technique which allows you to just use a counterexample rather than just a full proof to hopefully establish this fact, which is called the contrapositiveness. Okay, and basically proving something that is the converse of this, equivalent, the complement of this, which is that now because from the graph to the P is usually very easy. From the P to the graph is it requires a lot of enumeration. So I still come from the P. I'm saying that if the pair are not deseparated in the graph, okay, meaning that they are dependent, okay, and then are they always dependent in the P? In fact, if this is true, then that is true. They are equivalent. Okay, maybe just to give you a little help, here I just use a graph to show that. You start with a graph, and you can use the factorization law to define a set of distribution, and that factorization law basically gives you a set of independencies, and we basically can have the I of F like this, okay? And then here we have the other set of independencies, which is directly from the graph, coming from the i's of G through deseparation, and then defining the distribution based on the deseparation independencies. So the previous statement in here were really asking, is this and this two sets equivalent or not? It's a little bit harder to ask. What the contrapositiveness is saying that if something is not independent in here, not deseparated in here, okay, are they always not independent in the distribution or not. Okay, so I'm not going to dive too deep into that, but you can guess the answer already, right? It is not always the case. Because even though I can always, we saw example, a small one previously already, even though that in the graph, you can basically have an absence of independencies. They are not deseparated, for example, like this, right? And therefore meaning that they are dependent. I can still, which actually leads to, a P of A and B, which is a P of B given A and a P of A, right? So this is obviously, dependent, right? But the counterpositives are basically saying that if this is the case where two random variables are not deseparated, are they guaranteed to be dependent in P? My statement is that it's not. I can engineer a joint distribution like this where the conditioning on A become dishonored by saying that if A equals to 1, I have the same table, and A equals to 0, I have another same distribution. Therefore, regardless of your choices of the A, my conditional of B given A remain the same. So this is doable, right? I engineer a distribution like this. So numerically, this allows the A and the B to be independent, right? Therefore, graphically having a non-deseparation does not always guarantee that you have a dependence in the distribution in the numerical sense. Okay, as long as you let the author to be arbitrarily tricky in picking their distributions. Okay. Although this is not very substantial, because typically, you either learn these numbers from the real data, or you really trust that the users are not trying to waste people's time by engineering some fabricated answers. Therefore, the statement now says like this: they are dependent in some distribution, but this sum is a very, very small unnatural sum. Okay. In the most natural cases, you do have the soundness and completeness in both directions. Okay. So we're still safe, in our daily practice, where the independencies and the graph separation or the factorization are all talking about the same thing. Okay. So the good news is that in most cases, we have this. Okay, so until now, I think we kind of established, the equivalence and also the transferness between the graph and the distribution. And in the future, we'll be interchangeably just looking at the graph, for example, without even putting any numbers or distributions for that. Or sometimes we could go the other way around. Okay, I think that's all. We have a few additional slices to talk about the uniqueness, which goes to basically the different ways of expressing the same independencies. You can read that for your own leisure, after the class. And then there are a few examples of composing very traditional graphical models, like a univariate distribution and a few other expressions like plates and so forth. I think I'm going to stop here and see you next time. Here is a walkthrough of the hidden Markov model in a more detailed fashion. The notations here are quite interesting, and I want you to take a look after class to make sure that in the future we're going to use these notations for all graphical models.